Good evening all. I will get started in a couple of minutes. Hi, good evening. We'll wait another couple of minutes. Maybe people will join and then we'll get started. Hi, good evening. Okay, we'll get started. So maybe people will join along. So this week the discussion was on KNNs and then binary decision trees, basically decision trees, bagging, random forest. So out of this we'll be discussing like a question from each one of them. If you have any further queries, or we can start with your queries, or if there are no queries, I'll start with some of the questions that I have here, so we can solve the questions along. So if you have any queries, you can ask them, or I can get started with the questions I have. Okay, I'll get started with the questions I have. Yeah. So the first one is asking about KNN, k nearest neighbors. So these are very straightforward questions. So you can just message in the chat box. So which of the following options are true? So in a KNN, is it an supervised or unsupervised learning algorithm? So the first one is false. So basically KNN is supervised because you are using labeled data set. So it can be used for regression or classification, or is it only used for classification problems? can be used for both. So what is the difference in the algorithmic point, from an algorithmic point of view, what is the difference that you will be using for a classification versus regression problem? So in a classification problem, so you'll be using a voting kind of, you take the majority vote. So out of your k nearest neighbors, whichever is the max, you just check how many of the votes are for a particular class and which one of them is the maximum, you would be taking that one. So that is the majority vote that you will be using for classification. And in case of regression, you will just take the mean value of the nearest ones, and that should give you the output for a regression problem. And how many learnable parameters are there in KNN? So we were calculating this for convolution neural networks and fully connected networks. We were calculating the number of parameters. So how many parameters are there in KNN? So basically, how many weights that you have to learn in a KNN? Is the question clear? So how do you train a KNN algorithm? So in that training process, are we learning any weights or any parameters? Zero. So basically KNN doesn't have any parameters that you learn. So what is a K then? The K is essentially a hyperparameter that you need to fix beforehand itself. This is not learned during the training process. K is a hyperparameter, and then it doesn't have any learnable parameters as such. So this is false. So this we have just discussed. In a classification problem, you just take the majority of votes. So yes, I was complete. Yeah. K is not a learnable parameter. Yes. So that K is a hyperparameter that you need to fix before itself. So now what happens if you have an imbalanced data set? So we discussed this previously on what is the difference between a balanced data set and imbalanced data set. So in a classification problem, if you have two labels, say if you have a binary classification problem, so if you have two class labels A and B, if your data set, training data set, has 50% each of label A and 50% of label B, then this type of data set is called a balanced data set. So an imbalanced data set is one where you have a different proportion other than this, say something like a 20% and 80%. This is an imbalanced data set. So if you have a data set like this and you train a KNN algorithm on that, would you expect any changes in its performance? Like would its performance be better, less, or it doesn't depend upon balance of the data set? So will the performance degrade in case of an imbalanced data set? Yes, no. So we discussed this previously in the context of gradient descent. So when you are using gradient descent, we discussed that if you have an imbalanced data set, then when you take the weight update will have most of the contribution to the weight update will be from the ones which have more samples. So in this case, B samples are more. So in the gradient descent, you will have more weightage for that particular factor. So the solution finally will be the one that has more weights. But that was in the context of using gradient descent. So does KNN use a gradient descent? Or maybe steepest. Does this use any optimizer? So I hope my question is clear. So basically, what I was trying to put here is we discussed previously, not using KNN, so ideally dataset balance shouldn't matter. Okay, so since there are no learnable parameters, so you don't have to do any optimization as such. So basically it doesn't use any gradient descent method, so that is clear. Now coming back to our question, so the balance of the data set doesn't impact in this particular way. So if you have gradient descent, you have impacted, but even without gradient descent, how does KNN decide to put a label for each of these sample? So if you have an imbalanced data set, what happens is there are more chances of finding one particular individual than the others. So if your query point is somewhere here, and say these are my nearest neighbors, if you have an imbalanced data set, the chances that most of the nearest point, whatever the neighbors are there, the chances are very high for them to be from this imbalanced data set itself, like from class B itself. Say originally if it was a balanced data set, if this is your query point, most of your points would either be something like this. Say if the query point is class B, this is what you would expect in a balanced data set. Everything is equally likely, but just because this particular query point belongs to class B, the chances of B around it is higher than A. So this is a scenario you would eventually end up with. So this is something that is good. But when you have an imbalanced data set, if this is your query point, the chances of finding the, B's are higher. So maybe I should reverse these things. So if this query point is of class A, then the chances of the nearby points being A will be higher than the nearby point being B. But now if you have an imbalanced data set, what happens is the chances of point B is higher. So you could end up in a scenario like this where all the nearest neighbors are actually coming from sample B, and the chances of you misclassifying this point A as B is higher. So if you have an imbalanced data set, using a naive KNN might actually give you more misclassification error. So how do you reduce this? So I think this is clear. So basically imbalance will increase misclassification rates in KNN. So if this is clear, so how do you reduce this? How do you mitigate this? So what did we do in the case of gradient descent? When we have the same problem in gradient descent, we came up with some solution. So what is that solution? Can you recollect the one that we used for gradient descent? So when you have an imbalanced data set and you're training your optimizer, so what did we do then? How did we decide the weight update for an imbalanced data set? One solution at that time, if I recollect correctly, was data augmentation. So basically generate more copies of the one that has the minimum. Say in this case, generate more copies of A so that you still have 50% of A and B. That is one solution that was proposed at that time. And then we also discussed another one. What was the second one? So the problem here is basically you are having less number of values from the minority sample, and all the samples are being given equal weightage to calculating weight update. So then we decided that if you could actually weigh each of these depending on the number of samples it has, so that whichever has the minority representation, you actually give more weightage to them in your weight update. That is what we have done. So we have done some kind of weighing which is inversely proportional to the representation in the original sample. So that way we were able to kind of come up with kind of mitigate this problem. So if we can use the same idea here, so can one of you comment how would I use the same idea here? The idea is to weigh your factors, use some weightage to overcome this. So how do I do that? Count the minority sample more times. The idea of weighing is something close to that, but we won't count it more times, so we actually come up with a weight. So essentially what we will do is, even in this scenario, say if this is your point A or this is your query point, and if the data set is properly done, most likely you will find all the nearest points to be A, and then you will also have B's. Since B is more, you will find more B's than A's. And this is my, say I use a different color. So this is my query point A, and everywhere is my actual data. So what happens when you do majority vote is, you just get 3 votes for A, and you get, here there are 7 votes for B, so you will classify this as B, which is wrong. So what we do now is, when we are counting, we put a weightage that is proportional to the distance. Or sorry, inversely proportional to the distance. So whichever points are near will be weighed more than the points that are farther away. So this way what can happen is, all these points which are very close to this one will have a very high weightage, and if all these points are B, then the chances are the query point could also actually be B. So in this case, say all of these are distances at say 1, 1, 1, and remaining B's are at a distance 2. So this will be reduced by a factor of 2. So this will again, okay, maybe 2 is not a good number, but if you scale it properly, you could eventually end up with this value being lesser than the value of A, and then the answer will be close to A instead of B. Is the idea clear? Yes. There are no questions, then we'll go to the next problem. So the next one is on decision tree classifier. So the problem says that you have, it has single feature, one input feature X. X varies, like is a uniform random variable. Okay, it's not specified, but let's say it varies from 0 to 1, and for all values of X less than or equal to 0.5, it belongs to class A. So this entire region is class A, this entire region is class B. Yeah, the first question is straightforward. So how many input features are required for this? Is you just have one feature X, so you don't need anything more than that. So the second question is, determine the optimal threshold for the binary split using Gini index minimization. So now the question is, say I wanted to use a decision tree for this problem, and say you have infinitely many, like your data set is infinitely available. So basically you can just sample from this uniform random variable to create your data set yourself. So you have some infinite data set. This will only simplify our calculation. The idea here is for you to get an idea on how actually this Gini index minimization works. That is the whole objective of this problem. So now the question is, in decision tree, the first step is to identify your split point for your threshold. When you have multiple features, you also need to identify your feature. So basically it needs two things. One, you need to select a feature. Second, you need to select a threshold on which you will split the particular node. So we will leave this for now. It's a single feature one. So the idea is to understand how the threshold is fixed. Say let's say I'll fix a threshold of say alpha. I don't know what the ideal value of alpha is. For this particular problem, required value of alpha is how much? The ideal solution would be 0.5, which is something that I will have to get after solving it using Gini index minimization problem. So how do I do this? Say x is my input, so I decide some split point. So whatever values of x less than alpha, I label them as class A, and whichever is say less than or equal to alpha, and whatever is greater than alpha, I will label them as class B. So this is my tree classifier. So what is my Gini index of my input x? So basically Gini index will tell you how impure x is. So x basically has both A and B. So okay, I'm not sure if you are familiar with the formula. I'll write it here. So Gini index of any particular data set, I'll just write x here, is essentially 1 minus sigma pi square, where I is your number of classes. In this particular case, you just have two classes, A and B. So for the original data set, for x, my input, what do I have? The probability of any, if I take any point from x, what is the probability that will belong to class A? Since it is a uniform random variable, it has equal chances for both class A and class B. So the probability for being class A is 0.5, and for class B also is 0.5. So this will give me a value of 0.5. So this is the impurity present initially. Now if I do this split into A and B, so what will be my Gini index for this particular portion A? So what is there in portion A is everything between 0 and alpha, and B is alpha to 1. So in this data set A, what is the probability that if I pick a random point, it will belong to class A? So I'll write class A probability and class B probability, or let us use a little. PA is basically probability that if you pick a point from this capital A, it should belong to class A. So what is the value of PA? Alpha. So okay, now we have to make a little more assumption. So let's say alpha is okay, say alpha is greater than 0.5, like as shown in this figure, alpha is greater than 0.5. So basically your 0.5 is somewhere here. So alpha is the total length of the data set, or basically something that is proportional to the total length of the data set. So out of this, only this portion is where you have class A. Anything greater than 0.5 is class B. So in this particular, like I partition my entire input data set into two sets. Maybe I should give different names so that, say I'll put a name L and R, left and right, and G of L is what I'm asking you to find. Maybe this will reduce confusion. So within L, what is the probability that a particular data point is of class A? So originally in my input data X, the probability of class A is proportional to the length of class A, that is 0.5. So if you apply the same logic here, like it is a uniform random distribution, and I'm saying you have an infinite data set, so you can continuously generate data in this particular data set. So what will be the value of PA? Is the proportion in this particular one. So this is class A and this is class B. So the proportion of class A is 0.5 by total is alpha. So out of alpha, 0.5 is for the class A. So similarly, what will be the probability of class B? In data set L is the remaining one. So that is 1 minus this. So essentially it is alpha minus 0.5 by alpha. So this gives you the probability. So you can substitute this to get the value of GL. Similarly, so what about GR? It's the same thing. The only difference is now instead of L, you will have it on So what is PA here? So in dataset R, what is the probability that if I pick a point randomly, that it will belong to class A? Zero. So basically alpha is greater than 0.5, so this entire thing will be of class B. So probability of class A will be 0. The probability of class B will be, yes. So the probability of class B will be 1 minus 0, so you have a 1 here. So if you see, this will give you a value of 0, which means it is a pure partition. There is no impurity, basically you don't have any mixes, everything is of, it's completely homogeneous kind of one. So now the question is, how will I decide my optimal split? So for that, what we need to do is, we calculate the total, it's like this entire partition, let us say I call this D, and the total value of gene index for the D data set is equals to the proportion of L times this, so fraction of L times G of L plus fraction of R times G of R. So basically this fraction of L is the proportion of data in L compared to the original data set. So just to say, it is NL by NX. So we have this length as alpha, so this will be alpha, so FR will be the remaining one, so that will be 1 minus alpha. So if you just substitute the values, you have alpha times G of R is 0 since it is a homogeneous data set. So now what we have to do is optimize this, like essentially we need to find the alpha that will minimize this. So all you have to do is dg by d alpha equal to 0, and from this you will find an alpha value that will be the optimal value. I am not doing this derivation here, but you can check here. If alpha equals to 0.5, you will have this value to be 0. So like if you just substitute alpha equal to 0.5, this will cancel each other, this will be 0, so you will have a value of 0. So that will be the minimum value, and you can also solve this yourself, but just giving the optimal value, so which is the same thing that is in the original data set, that is what we require. So by minimizing gene index, you will be able to identify exactly which threshold you have to do. This is for a single feature. Now when you have multiple features, what you have to do is, you have to select one by one feature, and for each feature you need to find the optimal threshold and find what is the gene index for of them. In this case you have a solution, but ideally you wouldn't always get gene index to be 0. Whichever is the minimum value is what you will decide that as the optimal split. So now the question is, how do you extend this idea for regression? So if you want to do a regression problem, so how will you, what is it that will change in this particular template that you have set up here? Okay, so what will change if it is a regression problem? So instead of identifying just the class label, you need to come up with an actual value for the particular input value. So how would you do that? Would you take a mean value, or do I change my function? So because gene index is this probability, which is something that you don't have, because here Pi is basically the probability that a given data point will be of that particular class. In regression problem, we don't have classes in the original sense. So I need to change my function itself. So which function will I use then instead of gene index? definitely not Gini impurity, because this needs the probability of each class, and in case of a continuous variable you do not have a value for this probability, so you need to use something different. So which one can you use? So what were we using in case of the normal regression problems? So in any typical problem we were using mean square error. So we would still go with mean square error. The only difference here is, yes, mean square error or R square. So we need some value like something that works on real numbers instead of the discrete ones like a classification problem. So any of these should work. So this is again straightforward. So now let's go to one step further. So if you have 3 classes, so the previous one was 2 classes, say now we have 3 classes. Basically it says x less than 0.3 is of class A, 0.3 to 0.6 is class B, and everything else is class C. Assuming that it follows a greedy approach, like it uses Gini impurity, like it's a classification problem, so it will use Gini impurity. Which of the following 2 trees would be more probable? So now when you are constructing a decision tree, there are 2 possibilities. The initially, if X is my data set, it could either choose something like this, anything less than, like finally if it identifies the optimal one, the solutions could be one of this. If it is less than or equal to 0.3, it will classify as A. Greater than 0.3, you again have 2 scenarios. It can be either class B or class C. So if it is again less than or equal to 0.6, it will belong to class B. If it is greater than 0.6, it belongs to class C. Say let us call this tree 1, decision tree 1. This could be one solution. The other solution is instead of splitting at 0.3, initially it could split at 0.6, and anything less than or equal to 0.6, you can have 2 possibilities. Again, less than or equal to 0.3, you can classify it as A. Greater than 0.3, you can classify it as B. Anything greater than 0.6, you can classify it as C. So this is the second tree. Like both of them are solutions, both will actually give us answers to the original problem. So if you use a greedy approach, so which one of these 2 will be the solution? A split with a threshold of 0.3, this is, okay, let's say this is my A and this is my B. So out of these 2 trees, which one will be the answer? So why are we discussing this point here is because even in the previous case we were assuming that you have an infinite data set and kind of assumptions which are not true in real sense. So when we use a data set which might have some noise as well, basically where you can have data which is not labeled correctly, in such scenarios you can have decision trees like this is not a unique solution, so you can have multiple solutions and your decision tree might actually give some other answer if you just change little bit of your data. So we have a name for these things. What is that? So basically if there is any slight change in your training data, your solution could actually be completely different. So we have a name for that. What is that? Here we ended up with both of them are actually giving right solutions, so it is not a problem, but it might not be always the right answer. So slight change in training data could actually change your model. We call this as your high variance models. In this particular case, both of them are actually giving the right answer, so you don't have any problem. But if it has noise and kind of stuff, then you might actually end up with different answers. So okay, now coming back to the question, so out of A and B, which one do you think will happen? Like what will be the basis on which you choose is ideally calculate it's the same thing, you calculate GA and GB and see which one of them is minimum. Whichever is minimum, that will be my answer. So how do I calculate for A? it's same as before, like what would be my final, okay, let me ask other question. You can calculate GB like we have just done before. So initially what will be my gx? Initially I have three classes, three possibilities. So you have, if I pick a random point, it can be from class A or class B or class C. So this will give you one value, 0.3, 0.4, so it's 0.6. That will be same in both the cases. So what about the step 2? This is where there is a difference between both of the cases. So if I am doing this particular one, GA of A will be 0 because you have a pure set here, there is no inhomogeneity. But however, for this particular branch, let's put a name for this. So I'll call it BCA, or I'll just call it BC because it has both B and C. Will be, what is the probability of B in the second data set? So B has a weight of 0.3 out of a total of 0.3 plus 0.4, or it could be C as well. C has the remaining ones. So this would give you a value of 9 plus 16, 25 by 49. So 1 minus 25 by 49. So similarly, if you do for the second case, GP of C is going to be 0 and GP of AB is going to be 1 minus the fraction of A is 0.3 by 0.6. Both of them are half-half. So you have, so this gives you a 0.5, and this is 0.48 or whatever. So okay, now I have the values here. So now which one do you think is the one that will be chosen by the algorithm, A or B? A. So we haven't calculated the overall thing, right? So this is GAA and GABC. So again we need to calculate the overall one for the split A. So how do I do that? So GA is essentially proportion of A times, and then you need to calculate proportion of BC times. So what is the proportion of A in this one? So it's 0.3 times it is a completely pure set, so you have 0. And the second one is 0.7 times you have a value of 0.48. Give you 0.336. So if you do the same thing for the second set, you have AB times AB, and then you have fraction C times C. Fraction of AB is 0.6 times the G value you have calculated is 0.5 plus the second one will be the remaining fraction, and it is a pure one, so you have 0. So this should give you a value of 0.3. So out of this, the minimum one is the second one, so it will choose the second split. So this will be the tree that you will be getting instead of the first one. Are there any questions, or is this clear? Clear. Okay. So this is with the decision trees. Now let's go back to okay, boosting. So here it says, the question asks you that there is a original data set S, and then you are training two models on S. So basically S is your data set. You have split it into two sets, S1 and S2. And then you are training two different models. On S1 you are training model 1, on S2 you are training model 2. So basically for model 1 you are using S1 as your training data set and S2 as your testing data set. And these are the values of the predicted values of M1 on S1 and S2, and the Y2 and Y22 are for M2 on S1 and S2 respectively. So how do you calculate the variance? So this is, say you have two models, M1 and M2, and you have two data sets, S1 and S2. You train M1 on S1, you train M2 on S2. So this is the training one. So what are we doing now? Now we are using this model to predict again on this data set. So when you use model M1 on S1, you got something like Y11. When you use 1 on 2, you got Y12, and this is Y21, Y22. So this is what is given in the question. So what is the first? The first part asks you to find the variance. What is the variance of model M1? How do you calculate variance? Is basically expected value of so you just have two points, so it will be straightforward here. So what will be the value here? The mean value will be, so, or I'll just write it in the normal way. How do you calculate variance of it? So it will go something like Y11 minus Y11 plus 12 by 2, and then you have Y12 minus the mean of them divided by n minus 1. You have just 2 points, so it will be 1. So this value will give you Y11 minus Y12 all square by 2. So this is straightforward. So I don't think this needs any explanation. Or is this clear? If this is clear, then everything follows as well. Yeah, I hope there are no questions in the math. So this is variance for model M1. So similarly, if you do for M2, it is going to be in terms of 21 and 22. So that is Y21 minus Y22 whole square by 2. So the first part is straightforward. Is this clear, or are there any queries? Okay, I'll take that as clear. So now the question asks you, so now I am creating a new model using this M1 and M2, M3, such that the output of M3 is chosen as average of 1 and 2. So basically Y31 is chosen as Y11 plus Y21 by 2. I'll write it here. So you are just taking average of whatever is the previous models. This is what you are doing in your bagging. So this is my third model. So what would be the variance of my third model? So like expressions is already given here, so you can just substitute it. So what will be the one you will be getting here? It will be something like Y11 plus Y21 minus Y12 minus Y22 by whole square. You have a 2 square times 2, so you have 8 here. So I can write it as, say, something like this. Got it? Okay. So till here I hope it is clear. So you have the variance of M3, you have variance of M1 and M2. So now can you comment on anything between the relation between these variances? So basically, can I see, okay, I'll just take these expressions here, or let's see here. So you have variance of M1, M2 and M3 here. So can I comment on anything about variance of M3 in terms of M1 or M2? can I say something like this: variance of M3 is less than variance of M1 or say M2? Is this statement right from these expressions? Or nothing can be said? Okay, maybe I should take it a little. So variance of M1 is given by this expression. M2 is given by this, and M3, if I expand it a little bit, I can write as square this is basically 1/4 of variance of M1 plus 1/4 of variance of M2 maybe. Can you comment now on whether, say, both models M1 M2, or let us simplify it further, let us say variance of M1 equals to M2, only in that particular scenario this can be simplified further. So what do you have here? So both of them will be equal to each other, this and this will be equal to each other, so we'll have half of variance of M1. So this is a special case when both of them are equal. So what happens if they are not equal, or let us say this is a very special case, but otherwise can I comment on anything about this M3 and M1? Or let me put question differently. So when will this be true? When will the variance of M3 be less than variance of M1? So we have the summation here. If this particular term is positive, so okay, if this is positive or negative, maybe now it can get simplified. So let's say if it is negative. So if it is negative, so that this entire term becomes very low, then in that scenario your variance of M3 will be less than variance of M1. So when will this term be negative? So what are these terms here? So basically y11 is your training. So if you recollect, so y11 is on my training, y12 is on my testing. Basically y11 and y22 are on training data, and this y21 and y12 are on testing data. So what I am saying is y11 has actually trained better, so it's a much better predictor than y12. So you have this a positive value, this will usually be a negative value because your training will be much better than your testing. So in that scenario, what is that we are expecting is this term will actually be lesser, so your M3 could actually be lower than M1. So in other words, exactly one parenthesis is negative. Yes, so if only one of them is negative. So in that scenario, you will have this quantity more or less to be less than your original variance. So in other words, what we are trying to say is if your original models itself have a little bit higher variance, basically this difference is something that is not zero. In that is what you call a high variance. So there is a greater difference between your training and testing data. Then if the original model is a high variance model, then by adding these two models, you are actually getting a model which is having a lower variance than the original models. But if the original model itself has a very low variance, so to say that these values are 0, if both of them are 0, then it could happen that you will end up with a scenario like this, you could end up in a scenario like this, where the variance after combining both the models is also very close to the variance of the original model itself. So even if you do boosting, then it is not going to be of any help to you. Is the idea clear? So basically the conclusion that I want to bring here is by combining the ones which are having very low variance, you are not going to get any benefit. So it's useful only when you combine several high variance models and then aggregate them. I hope this is clear. Are there any queries? Got it. Okay. Okay, after bagging, the next question is on random forests. So this should be straightforward. So first one is how does a random forest does the final prediction? Does it take an average over a random set of predictors? So okay, let me ask the question in different way. So there are two things. One is boosting and random forest. So what you do in boosting is you train several decision trees and then you take an average of them. Like basically you train on a bootstrap data set, you train several decision trees and then you aggregate all of them, say you do average of it and then you get the final answer. That is what you do in boosting. So random forest is also similar to it. So what is the difference between both of these? I think the answer is already there in the question itself. So let's see, let's go one by one option. So what do you think about the first option? How does a random forest predict the final answer? It has several predictors, it trains several predictors, it takes an average of all the predictors to get the final answer. I think you agree with this point here. Are there any questions on this first point? I don't think there will be any questions on the first point. So the second and the third points are where there is a difference between boosting and random forest. So in boosting as well as in random forest, you do not train your entire, you do not use your entire training data to generate one particular predictor. You use only parts of random subsets of the data to train different classifiers. So this is clear. This is where the difference comes. So previously in boosting, we have been always selecting all the features, but in random forest, we will only select a subset of features. So if you have 100 features in your training data, you randomly choose say 20 of them, and say if you have 100 features and 100 samples, or let's say different number, say 200 samples. So your data will be of say size 200 rows by 100 columns. So this will be your data set, input data set size. So what we do in random forest is we select partially of it. So we select only a few samples from it. So let's say 20% of it or say 10% of it. So we just say 10 samples, and then you do not choose all the features. You choose only say another 10% of it. So we just learn only 10% of those features. Only use this particular data set to train your model. This is what you do in random forest. But in boosting, what we were doing is we only train on 20 times we use all the features. This is the only difference, that minor difference that you can see. Is this clear? I hope this is clear. So what about the last one? They are more prone to overfitting than a simple decision tree because of randomness. So now what we are saying is instead of selecting all the features, I am randomly selecting some features and I am making my data set. So because of this randomness, is it going to be more prone to overfitting? Yes or no? We discussed something very similar, very close to this one previously, something called dropout rate in CNNs. So even in the dropout, what were we doing? When you have CNN, we were essentially, when training the weights, we will not use all the weights. We certainly drop some of the weights and then we learn them, only the remaining ones. So this is something, the idea is very similar here. Yes, this is false. So the idea is very similar to a dropout one. So by introducing randomness, instead of training on all the features or instead of training on all the weights, you only take a subset of them and train only on those particular ones. This way you are actually, your model is actually robust to new ones. So that way you are not increasing your overfitting. So basically you are trying to increase your generalizability with this randomness. So the last statement is false. Okay. The next one is on gradient boosting. So what do we do in gradient boosting? Okay, the question asks you that if you are using a mean square error as your objective function and you want to use a gradient boosting regression, it's a regression problem. Out of these two statements, which of the following is true? The first one is regression trees are fit on the residuals of the current ensemble of learners. The second one says the trees are fit on the negative gradient of the loss function. So just to recap, so if x is your input data, what would you do in a gradient boosting? Or you first train a model. So let's say you're training some model W1 and then you get some value, say y1 hat. Once you get this y1 hat, so what is objective function here? It will be something like you will be trying to minimize y minus y1 hat square. That is what is given. It minimizes the mean square error. So let's call this as R1. So you're basically minimizing R1 square. So now what you do next in gradient boosting is you take the same x as your input, but you train another model W2. Say that model is predicting y2 hat. So what will be you will try to minimize something. What is that something here? What will you try to minimize here in gradient boosting? Is it going to be y minus y2 hat square? Yeah, you are going to minimize the residual. So is this the residual, the one that I have shown here? So y is my actual output, so x is my input and y is my output. So is this what you will try to minimize for your second model W2? So when you use your gradient descent for W1, like say W1 is some, it could be any model. Say W1 could be, say let us say neural network or a decision tree, any model you want to try your, like it could be any model. Let's say it's a neural network. So if you want to update the weights of that particular neural network, you need to apply a gradient descent on an on an objective function, and you have chosen this as your objective function. So the first part is clear. So once you train W1, now you are using the same data set X and then you are training a different model W2. However, the weights of this model are learnt on a different objective function. And I am saying that is this the objective function? Yeah, you are mentioning it's on the residual. So is this that particular residual you are talking of or something else? So okay, you are saying residual. So should I put R1 square instead of this or something else? So basically you will try to minimize on the, I think you are trying to say that you want to minimize residual in terms of this is the R1, the actual R1 versus whatever you are predicting. I think this is what you are trying to say when you want to minimize the residuals instead of R1 square. R1 square is already minimized in the top. So basically I think this is what you are referring to. you'll try to minimize r1 minus y2 hat square. So this y2 hat, you will try to predict this error, so that when you add them back to y1 hat, you will get the original, like your predicted value will be close to the actual value. That is the idea in your gradient boosting. So this is what you will be predicting in the next step. So if you come back to the question, so the first part says that it's fit on the residuals of the current ensemble of the learners. So that is what you were saying. So what about the second option? So it is fit on the negative gradient of the loss function. What is my loss function? My loss function, say in the first case, is y minus y1 hat square. So negative gradient of this will be basically the idea is very similar. So in this particular case, when you have a mean square error, it so happens that if you take gradient, you will end up with having the residual again. So both of these statements are identical to each other. So you will again, by actually minimizing your negative loss of the gradient, you are essentially minimizing your residual. So both are equivalent only for this particular loss function. It so happens that even if you use the binary entropy, you will end up with the same scenario. That is something that was already discussed when we were discussing on neural networks. Is this part clear, or are there any queries? We are like halfway into the session, so are there any queries up until now? Okay, I take that as no. Okay, if there are no queries, then clear so far. Okay, thanks. The next one is on AdaBoost classifier. So since the question is already asked in the assignment, so I am not going into the mathematics of it. So this is a very simple, straightforward question. So is it more prone to overfitting? Because you are using, the idea is very similar to the previous one we discussed. When you have a very high variance model, and then you are combining lot of these high variance model to generate a model which will have a lower variance than the original models. This is very similar to the one that we discussed previously in case of boosting also. This is the next point that requires attention. So here it says that it reduces the model prediction capability if the ensemble is made from strong learners. So basically, if the weak learners, essentially the weak learners, or W, say, if these weak learners are low variance models, and I have combined all of those weak learners to make my strong learner. So let's say E is an ensemble of these weak learners. Will the variance of this model be higher or lower than the original one? One thing is clear, if Wi is high variance, then variance that you obtain by combining all of them is going to be less than the original ones. So this is clear. This we have discussed in case of boosting. So what will happen in this particular scenario? So in the case of boosting, what happened was, if you use the models which have very low variance, then by adding all of them, you are not going to get any improvement in your variance. So there is no point in actually adding low variance models and getting better prediction accuracy, something that is not possible with boosting. So do you think that the same thing will happen in case of AdaBoost also, or will it be different? Of course, you can say, like, since I am asking the question, it will be different, but you have any intuition or something that says that this or the other one can happen? Let's say this is 1 and 2. So which of these two statements will be true? So So how is AdaBoost different from boosting? In boosting, what we were doing is we are splitting the training data set, and then we are training several weak learners, and then finally we are doing an aggregation where you sum up all of them and then come up with your final one. However, in AdaBoost it's slightly different. So when you are training your weak learners, whatever data that has been misclassified will actually be given more weightage, like the one we were discussing on gradient descent. So when you give more weightage to the misclassified data, the next learner in the gradient descent, that particular weight update will be much higher for these misclassified points. So the second learner will actually learn more about these misclassified points than the original ones. So once you have these two models combined, and then you have mislabeled points, for that again you train another classifier only focusing on those mislabeled points. So when you add all these ones, so eventually you will get a better model. So with this logic, even when the original ones have a low variance, by combining all these low variance models, you are at each further step you are actually trying to increase it. There is no way it could actually be lesser than the previous one, which is not something that is happening in boosting. In boosting, you are just doing a normal aggregation. You are not giving any special preference for why you are missing out on some classification points or something. That is why in boosting, if the weak learners are actually low variance models, then you would not get any improvement. This is not the case in case of an AdaBoost, because here you get an incremental So basically the second one is false. So is the idea clear, or basically the intuition is clear? We will not go into the math of it, but I think the intuition should be clear. So this is the last problem for this week. So the last one is on k-means. So it's a straightforward question, so you can quickly answer if you already know. So the first one is, it supervised or unsupervised classification algorithm. So basically, in order to train this model, do we need a labeled data set or not? It's an unsupervised one, so this is false. Again, so how many learnable parameters are there in the k-means? So in KNN we discussed that it doesn't have any learnable parameters. So the idea will be very similar even here. So the k is something that you have to provide before actually training that one. So this is not a learnable parameter, k is a hyperparameter. So this is again a false. How does it do the inference? By inference I mean like when you want to predict the label of a given class, so you give some input data, it will actually throw out some output. So that is what you are calling inference. So that will be very similar to KNN, yes or no? So it's like you just identified some cluster, so you just take the, if a new data point is given, it will again see the nearest ones, and then it will calculate the mean of that. Whichever mean is it is closest to, it will give that as an output. So the idea is very close to KNN. So this is true. So the last one is something that I want you to pay a little attention. So it can be used to generate new features. So what do I mean by new features here is, why do we need k-means, or for that matter any unsupervised classification algorithm? So where do we like, can you point out any one application where you use unsupervised classification? Maybe I can give one example. Say you have some data set and then you know that data set has some noise. Basically the data set has some incorrect labels in it. So people typically call them anomalies or outliers or whatever name you are familiar with. So in the given data set there are some points which are actually anomalies, but you cannot identify them beforehand itself. So your original data set, say at a particular data point is of class A, but because of some typo or whatever, it has been labeled as class B. This is what you are calling an outlier or anomaly. So things like this could actually be identified using this unsupervised classification. Say for example, which example? Okay. say you have temperature and velocity, and say PM, I don't know if you are familiar with PMV, or let's say some comfort index or something. So if temperature is say 35, and maybe instead of velocity I'll keep humidity is say 60%, you're say comfortable or something. Whenever it is 25 and say it is 60%, you are comfortable. Whenever it is 24 and say 70%, you are comfortable. Say 35, you're not comfortable. 35, 50, you are not comfortable. So you have some data set like this. So out of this data set, what the features are basically TH and comfort index. So what you would like to identify is there any anomaly in this particular feature? So if you see this particular data point, 35 and 60%, it shows as this. However, the other one, like when it is 50%, it shows as uncomfortable. So like we can actually directly tell that the temperature at 35 is something that we are not comfortable with. But when you train the model, like you want to predict comfort index directly. So if you want to train a model that takes T and H as input and predicts this whether you are comfort or not, like basically it's a classification problem. So it will tell you whether you are comfortable or not. So F is the model that you are training. So if this is the only data set that you have and you train your model on this, then obviously the model is giving like say you have your training error is 0 for the particular model that you have chosen, then when you give this particular input, it will actually tell that yes, comfortable, which is actually a wrong answer. So what we want is a filter before actually feeding that into this particular model. So how do we train that filter is where things like this unsupervised classification will be useful. So in unsupervised, what it will do, it will see within the data itself, it will understand the features and it will try to create its own representation into two different classes. So if you use k equal to 2, it will split the entire data set into two features such that this 3560 will actually come into one class and remaining everything will come into other class. So whenever this particular thing comes, it knows that this is something that could not be used for training. So this can be used as a filter kind of one. This is one application. Is the idea clear? So basically what we will do here now is from this we will generate again another feature. The new feature will be saying like another feature saying the say y or something. So this y will essentially tell you whether they say reliability of the data or something. So the first point is not reliable and everything else is reliable. So when you add this extra feature and you train your model based on this extra feature, then it might give you better results than the original one. Is the idea clear? The same idea will again come later when we discuss on autoencoders. Even there you try to create new features in such a way that will represent the original data distribution as well. So we will discuss that when autoencoders come. So yeah, so these are the questions I have for this week. So I think we have covered most of the parts. So are there any other queries that you want me to discuss? Yes, low or high variance, it will increase your performance. So maybe the next question would be why not use AdaBoost always? Is that your next question? Yeah, maybe I'll leave that as a homework kind of problem, so you can just see why not use AdaBoost. You can try it and it works most of the scenarios. Most of the papers do like implement AdaBoost in their final step. So they develop their own model, they try 2-3 different models and finally they'll use AdaBoost to combine all of them. That is what people have been trying to do. Like it's already been done. They always use AdaBoost finally. So like essentially you use 2-3 different models. Say for the same problem you use a decision tree first, and then you use a convolution neural network or something for classification, and then say normal neural network, a decision tree, and then you combine both of them. Or you can use so many decision trees, or you can use so many neural networks and combine all of them finally using some of these algorithms. These ensemble methods are one class, like people have been trying, they are using these things from a long time. So any other queries? Fine, then if there are no queries, then maybe we can conclude the session for this week. I'll keep the forum open for discussion. Any queries if you have. If you do not have any queries, feel free to leave the session. Yeah, I think there are no questions. Yeah. Thanks for joining. We'll meet next week. Thank you. Yeah, I'll end the session then.